We're privileged today, let me welcome Dr. Jaime Barnes, who is the Geoprism lecturer, or one of the Geoprism lecturers this year, and she'll explain about Geoprism here in a moment. And she'll also be our distinguished lecturer here tomorrow, so there'll be a more general talk that Jaime will present tomorrow afternoon in our regular DLS time. So Jaime's an associate professor at University of Texas. She started there in 2009. She did her PhD with Zach Sharp and Jaden Silverstone at New Mexico. Reading from her website here, she's interested in a broad spectrum of geochemical applications that include stabilized type geochemistry, volatile cycling, metamorphism, and volatile transport in subduction zones, serpentinization, fluid rock interactions, metasomalism in high temperature regions, environment. Much of her research utilizes stabilized types, I'm actually for some of those things here today, as geochemical tracers of fluids in various tectonic and geological settings, all the way from the upper mantle through the plate lithosphere on up to even forearc thermal springs and volcanoes here. And she includes in here studies of halogen and halogen isotope chemistry, like chlorine chemistry here. So it's a real pleasure to welcome you here, Jaime. So.
Yeah, thank you for the introduction. Thanks for inviting me to come, and I also want to thank the National Science Foundation and Geoprisms that helped funded some of this work. And Sean indicated that I can tell you a little bit about the Geoprisms program. It's a wonderful community of scientists and researchers that falls under the umbrella of the National Science Foundation, and essentially they're interested in questions related to plate margins. And there's one part of it that's focused on subduction, and there's another part of it that's focused on rifting. And it brings together geochemists, petrologists, geodynamicists, and geophysicists that are all trying to address similar questions from very different perspectives and try to have a multidisciplinary community in order to answer some of these large questions related to plate boundaries. And some of them are related to focus sites. So one of the focus sites is the Hickory margin in New Zealand, which I'll talk a little bit about today. And then there's also just general science questions that will fall under the umbrellas of geophysics. So today, for my talk, I wanted to talk about the role of the forearc in volatile cycling through subduction zones. So the first half of the talk is just going to be particularly looking at volatile cycling through subduction zones, mainly thinking about halogens, which I work on a lot, but also a little bit about lithium and boron, kind of what we know, where we are in terms of the science, and then end with what we don't know. And one of the things I'm going to argue that we don't know very well is actually quantifying volatile cycling through the forearc. And so then the second half of the talk is going to be thinking about the forearc, looking at Cascadia, and then also in New Zealand. And so this photograph that I have on the cover of the slide, this is a cold spring and the forearc of New Zealand. This is called Mangapakia. In this slide, I didn't put a scale in here on purpose because it looks more impressive than it is, but it probably comes out to a little bit above my feet. Yeah, and Stuart knows these well. And before I get started, I also wanted to acknowledge a lot of my co-authors. So throughout the course of this work, I'm going to be presenting some work that I've done, and none of it would have been possible without my co-authors. And so I'll try to not name them all now, but bring them up as we go along throughout the talk. And then particularly when we talk about the new work in New Zealand, I'd like to issue a very special thanks to the numerous New Zealand landowners and also to the EV Council that gave us permission to collect samples on their own land. Okay. So to begin with, like I said, the first part of my talk is going to be looking at an overview of volatile cycling through subduction zones, primarily focused on the halogens and also lithium and boron. So I want to start off by looking at inputs into the subduction zones, both by means and amounts. So where are the halogens sited? Sediments, altered oceanic crust, serpentinites, and then the amount in each one of those different reservoirs. Then we're going to look at volatile loss, halogen loss during subduction. So looking at volatile loss during prograde metamorphism and consequences for that loss. And then we're going to end up by looking at outputs from subduction zones, mainly by looking at outputs from arc volcanoes. both in terms of means and amounts, doing a little bit of mass balance calculations, and then trying to figure out, well, what do we know and what do we don't know? What are the gaps? But before I start, I want to talk about why do we care, particularly why do we care. We're going to talk a lot about halogens today, so why do we care about halogens? So this is from the Deep Carbon Observatory website. So they're highlighting a paper, and they're asking, in this paper, they're asking, did a burst of halogens kick off the end of the Permian extinction? So directly following a massive and a prolonged series of volcanic eruptions about 250 million years ago, at the end of the Permian, extinction began. It's one of the most severe extinction events in Earth history. And so this group analyzed rocks that came to the surface before and after those eruptions, and looking at their halogen budgets. And what they showed is that they unleashed a large stockpile of halogens, which we argue that were trapped in the lithosphere, that went into the atmosphere, that eroded the ozone layer and contributed to this mass extinction event. So this is highlighting some of these works by Broadley and others. And so one of the points is halogens can actually cause mass extinction events, but essentially the cycling of halogens can affect the chemical evolution of different reservoirs on Earth. So one of the reasons that I'm interested in halogens is that they love water. They track with water, and so they're very hydrophilic, and so we can use halogens to trace the movement of water. They also affect the transport efficiency of different trace elements, particularly metals. So chlorine in particular likes to complex with metals, and so it can transport metals. They also change mineral stability fields, so it lowers the water activity and allows dehydration reactions to occur at shallower depths. And like the example that I gave before is that it can influence the chemical evolution of the mantle, the oceans, and the atmosphere. So to understand if we're putting more halogens into the mantle or more halogens into the atmosphere has consequences for its chemical evolution. So if we just start off by looking at what are inputs, halogen inputs into the subduction zone. So here I've done just some very basic pie diagrams looking at average concentrations of these different elements, so chlorine, fluorine, bromine, and iodine, looking in sediments, altered oceanic crust, which is AOC, and then serpentinite. I don't have sedimentary pore fluids here, because here I'm just assuming that most of the sedimentary pore fluids are squeezed out at relatively shallow depths. And we're starting, there's still some unknowns, particularly in terms of bromine and iodine, but we're starting to get a pretty good handle on where these different halogens are hosted. So serpentinite can, on average, has about 1,000 ppm chlorine in it. There's also some in altered oceanic crust, primarily locked up in amphiboles, and also some go into sediments. More fluorine in sediments, but you can also get some in altered oceanic crust and serpentinites. And then sediments are a large host of bromine and iodine, primarily in organic matter. And it's recently been shown that serpentinites can be a pretty large reservoir of iodine, so iodine can go into serpentinites. So that's just in terms of concentrations. And then if you make some guesstimations or averages, assumptions as to how much is being subducted globally, thinking about average sediment thickness, average convergent rate. Here I'm assuming that there's 5% serpentinization of the oceanic lithosphere. You can start making mass balance calculations to look at total input fluxes. And so depending on how much assumptions of serpentinization of the oceanic lithosphere there is, that serpentinite pie is going to get larger or smaller. Okay? But in general, altered oceanic crust primarily hosted a lot of the chlorine and the fluorine in terms of locked up in amphiboles, where bromine and iodine have a large amount of, is largely locked up in sediments, and then some of the iodine in serpentines. Okay? And so we're getting a pretty good idea of what is going down. And folks have actually used halogen ratios in order to try to place constraints on the compositions of different reservoirs. So this is a compilation that been modified from previous work by Tim Yon and Mark Kendrick. So just looking at fluorine and chlorine and iodine and chlorine ratios and bromine, chlorine and iodine and chlorine ratios. And what they show is that sediments fall in a particular area, sedimentary pore fluids, which are these small dots, have a particular trend that you see. And so later on, when I start trying to use halogen ratios in order to track different reservoirs, we can go back and look at some of these figures.
Excuse me.
Yes?
Can you go over the explanation? What's the difference between the sediment concentration in this element and the sediment pore fluid concentration?
Right, so the sediment, so the question was, what's the difference between the halogens that are hosted in the sediments versus halogens that are hosted in the sedimentary pore fluids? Yeah. So the sedimentary pore fluids are just the fluids in the spaces between all those sediments. And so most people assume that those are squeezed out at fairly shallow levels, like less than 15 kilometers from the subducting slab, and they don't survive to depth within subduction zones, although some people would disagree with that. Yeah. Okay, so we have a relatively good idea of inputs, but then the question is, what percentage of these halogens are actually reaching depths of arc magmagenesis, and any of them reaching beyond that? Okay, so what is being lost during subduction, and how is that being modified? So this is some work. This is a figure from a recent review paper that was put together by Marco Scamboluri. And so he's looking at halogen loss from serpentinites. And so we have our abyssal serpentinite, which can have high concentrations of chlorine and iodine. And as it gets subducted, you go through these different phase transitions. So you start out, here's temperature on the x-axis, pressure on the y-axis. Then you go from chrysotile to antigerite. Antigerite breaks down and forms olivine and brucite. And then all the way up here to where you get olivine and gets water. And so how are the halogen concentrations of the serpentinite changing as you're increasing temperature and pressure? And so this is a figure from Marco in which we look at boron concentrations on the x-axis, chlorine concentrations on the y-axis. So here would be a mantle olivine with relatively low boron and chlorine concentrations. You serpentinize it, and so you enrich it in up to 1,000 ppm chlorine, 100 ppm boron, and then with prograde subduction, you start to lose that chlorine and boron. Same thing here, I've got chlorine concentration. So you start off with about 1,000 ppm chlorine on average, so this is some work from Aerotobio, down to about 10 ppm chlorine. So you've lost most of it, but some of it is still left behind, a little bit. This is some recent work that I've done with Greg Bebout, Sarah Peniston-Dorland, and Philippe Agard, looking at halogen loss through sediments and metasediments, looking at the Catalina schist, the schist of Estrella, and Marca Beachiana. And so here we have a very schematic diagram of a subduction zone, but we looked at chlorine and lithium, average concentrations in seafloor sediments. And as you increase metamorphic grade, what we've shown is that you reduce the amount of lithium by about half, right? This is just based on 1 suite of rocks. But you've lost most of the chlorine, but you're still getting some down to depths of arc magmagenesis. In terms of altered oceanic crust, there's been much less work done on that, and so actually I'm a PhD student who's currently working on that. So we know that with prograde metamorphism, by looking at exhumed metamorphic rocks, we're starting to lose some of those halogens. And I just presented some of the chlorine. We know less about bromine and iodine, but we know that we're losing some of those halogens. And then the question becomes, well, what is the consequences for that loss? How is actually changing the chemical properties of the fluids that are coming off the slab? So if we think just in terms of chlorine, you start to make these very saline fluids due to this chlorine loss. Some of the consequences of that is it can delay the onset of slab melting. Your dehydration reactions are going to occur at lower temperatures, so shallower depths. And then if you have enough chlorine and enough CO2, you can create a large miscibility gap and create a brine, which becomes important because it has the ability to transport metals. And so one of the questions that I was interested in, and this is some work that I've done with Craig Manning, is what are the effects of subduction zone pressure and temperature on the concentrations of different dissolved solutes? And so I really have to thank Craig for the next several slides. So one of the things that he did was to do some thermodynamic modeling to try to understand what the different species abundances are in a 1 molar solution of potassium chloride and sodium chloride in different subduction zones. And so what he did was to look at Alaska and Cascadia. So he picked more of a warm end member subduction zone, so like Cascadia, more of a cooler end member subduction zone like Alaska, and then looked at the thermal gradients using Ellen Syracuse thermal models. And what he did was to look at, as temperature increases, what is the concentration of different components in these solutions. And so what he sees is that sodium and chlorine are the most predominant species along the geotherm, and I should say this is looking at the top of the sediments. And at higher temperature at a given depth, you get more ion pairing. So if you start to compare Cascadia to Alaska, slightly more ion pairing. Okay, in the warmer subduction zone, same thing here. This is potassium chloride is slightly higher than Alaska. And so we became interested in that because what does that mean in terms of elemental transport? And so this is just looking at the addition of chloride. Same thing, we're looking at Alaska and Cascadia, temperatures on the x-axis, located on the y-axis. And so the addition of chlorine, he sees that you increase the amount of metal that you can transport. And you would expect more or higher concentrations in the warmer subduction zones. So that's one of the reasons that we should care about what the composition of those fluids are. And then the next little bit is looking at what halogen outputs are from subduction zones. Most of this is done by gas data, so measuring volcanic gases coming out of active volcanoes like HCl, HF. But folks have also looked at halogens and olivine-hosted melt inclusions from arc basalt. So this is a compilation of a lot of data from other folks. This is not my data. And what they did, I made a compilation. So chlorine is on the left-hand side, fluorine is on the right-hand side. The gray line is more. And so I've got different subduction zones, and I've highlighted some different volcanoes. But the point is to show you that fluorine and chlorine are all elevated above more. Okay? And so this is a common argument, as strong evidence for slab-derived fluids reaching down to the depths of archenegenesis. So we know that we're losing some halogens along the subduction path, but we're still able to transport fluorine and chlorine down to depths of archenegenesis. So then I made this relatively ugly slide, but so trying to look at mass balance calculations. And so on the y-axis, I have arc inputs in grams per year for fluorine, iodine, and bromine. So these are based on those calculations with those pie diagrams that I showed you at the very beginning. And then we have arc outputs on the y-axis in grams per year. Most of this is based on volcanic gas data by other people. One of the studies is based on melt inclusion data where they then try to scale it up. And so it's actually interesting, the melt inclusion data matches with the gas data relatively well. The black line is a one-to-one line. So where they overlap, if they're below that one-to-one line, it means that there's more inputs into the subduction zone that is coming out of the volcanic arc. We're only looking at the arc front here. And if there were overlap up here, then that means that there'd be more coming out of the volcano than that's going to be input. So for these four different elements, chlorine is slightly below the line. Fluorine is pretty far below the line, and bromine and iodine are also pretty far below the line. So what does this tell us? If you just look at outputs from the arc volcanoes, and we're assuming that all of our assumptions are correct, chlorine is the most efficiently recycled. That means most of the chlorine that goes down comes back up. Okay, so we're not recycling that much chlorine into the mantle. What's interesting is that fluorine is one of the least recycled, okay? So does that mean that we're putting more fluorine into the mantle, or are we actually missing something? And so there's several other authors or researchers that have pointed out that chlorine and fluorine are decoupled from one another. which is a little surprise to me at the beginning. It seemed like they should be the same, and we don't actually know why. A lot of people have argued that it's due to mineralogical controls. So fluorine will prefer to go into normally anhydrous minerals than chlorine. And so maybe you're just sequestering more of the fluorine in these non-anhydrous minerals and the slab residue that can make it down, or maybe it's locked up in minerals like titanium or climate. So, but most of the arguments have been about mineral host. In terms of iodine and bromine, does this mean that there's more iodine and bromine going into the mantle? Some people have argued that, but a lot of people think that this is just very shallow loss of bromine and iodine in the forearc that's not captured in any of these outputs. I don't have boron on here, but boron behaves very similarly to chlorine. It's largely recycled back to the Earth's surface. So what goes down comes back up, thought to not be putting that much boron into the mantle. And for lithium, it's less well understood. But we do know that there are halogens that reach past the depths of arc magnetogenesis. And we know this by a few studies, and again, this is a compilation of other researchers that's cut off on the bottom. But looking at concentrations of halogens in back arc basalts. So here I have chlorine, bromine, fluorine, and iodine from different back arc basalt classes. The gray is more, and the point of this slide is to show you that all of them are higher than more. And so there are some halogens that are making it past the depth of arc magnetogenesis and then are getting transported into the mantle. So we go back to this introduction slide again, and then the question is, so we're starting to get a pretty good handle on inputs into the subduction zones and the concentrations and the amounts. We have a pretty good idea of arc outputs, but the question then becomes, what are we missing? So we're just, when we do these mass balance calculations, everybody, including me, have just looked at inputs and outputs from the arc volcanoes, and is that a good way to think about things? So what are we missing? I would argue that we still don't have a very good idea of what is being lost from the subducting slab during prograde metamorphism, and that we still don't have great constraints on this deeply subducted residue, at least in terms of the halogens. We also are not sure about the amount of halogens that are sequestered in the lower crust or the subcontinental lithospheric mantle. So what's getting stuck in between, and what is the residence time? So there's been that one study that I showed you that looked at halogens and xenoliths. So how much is getting stuck in between? And then for the rest of the talk, I'm actually going to focus on the forearc. Okay, and so what is actually getting short-circuited through the forearc in either thermal springs or cold springs, and that we're completely missing from these mass balance calculations. Does anybody want to ask any questions midway before we switch gears a little bit? Yeah.
Does that mean that the mold are more degas than the arc magma just because the final pressure of melting is lower, and so you lose more halogen just at the end, actually, of the melting current?
So the question is, are you degassing any of the halogens?
Yeah, but so the fact that the mold showing that this very low value, would that be just because there are more degas?
Oh, right. So that warm data, those estimates are based on what they would argue we have those have very little halogen loss. Yeah.
Okay.
Yeah. Yes. Stuart, can you?
So when you showed that change in the chlorine content decreasing as you were going deeper down the subduction slab, or the work you did in California.
Yes.
So you made no comment as to where the chlorine sits mineralogically.
Yes. Yeah. Yeah. So, so there's been a little bit of work, at least in terms of the metasediments. A lot of it is in the chlorite, and a little bit in white mica. But yeah, starting to do some more detailed work on what the mineralogical host is.
But so basically it's a transformation of a clay or a mica giving off as
Right.
it gets
Yes.
transformed to something.
Right, and
Some mineral that don't accommodate chloride.
exactly,
Okay.
right, and if it's then completely lost from the system, or if it can then go into something
And that
else.
same with the olivine to serpentine back to
Yes,
olivine.
yes.
My question is, fluorine and chlorine, you showed that fluorine is at ppb level, whereas chlorine is at ppm level, but
Yes.
do they have the same amount of effect on like the chemical state or?
Oh, yeah, so at least in terms of the modeling that we did, we only looked at chlorine. Partly just because there's more information. Out of all the halogens, chlorine's the one that has the most information. Yeah.
So it's not like you only need a little bit of fluorine to have the alternative chemistry.
Right, yeah, I just don't know. Yeah. Okay, so the rest of the talk's gonna be thinking about halogens and a little bit of lithium and boron also through these forearc springs. And so our volatiles and forearc, so one of the things that I needed to first figure out is that when we look at volatile loss of the forearc, are they telling us about source from the subducting slab? Or do we need to worry about what I'm going to call process or local fluid rock interactions? So when I measure the chlorine that's coming out of these cold springs and hot springs, is this just chlorine that's coming from the local rock, or is this actually chlorine that's coming from the subducting slab? So we first need to tease out that. So here's my exaggerated forearc. So the first place we're going to go is Cascadia. And Cascadia is located, we looked at springs that, they're thermal springs, so hot springs that are located about 60 to 80 kilometers above the subducting slab. And then the second place we're going to go to is New Zealand, primarily looking at cold springs, and these are looking at the very, very shallow part, about 15 kilometers above the subducting slab. So this is some work that a master's student of mine, Jeff Cullen, did. And so he was looking at 28 thermal or mineral springs along Cascadia, and on this map right here, these dotted lines represents the depth to the subducting slab. And so these thermal springs are located all the way up from Washington down to Northern California. I should say that this was also work that was done in collaboration with Shel Hurwitz at the USGS and Bill Beeman. We also looked at a suite of very well-characterized lavas that Bill's done a lot of geochemical work on in the forearc to understand what is the chemistry of the rocks that these fluids could be interacting with. And so there's been some work done on these forearc springs before in Cascadia, primarily from folks from the USGS, and one of the things that has been pointed out is that they've got really high concentrations of chlorine, and what is the source of that chlorine? So the first thing that we did was look at the oxygen and the hydrogen isotope compositions of the water, and their meteoric water. This was expected, this has been previously shown. But some of these springs have up to 19,000 parts per million of chlorine. So the question is, where is all this chlorine coming from? We look at the chlorine concentrations in these lavas. They're much, much lower, so anywhere from about 20 to 160 ppm. So one of the things we did was to look at the chlorine isotopes. We looked at chlorine isotopes in order to try to figure out what the source of the chlorine is. The values of the water range from about 0 to 2 per mil, where the values of the lavas, the host lavas, range from about 0 to about 0.8 per mil. And so on the x-axis here, this is the chlorine isotope composition. The green line is 0, so this is seawater. This is 2 per mil over here, and then this is latitude. So we're starting up in Washington and going down to Northern California. The blue squares are springs with high chlorine concentrations, so greater than 1,000 ppm chlorine. The red circles are ones that have low concentrations of chlorine. And so you can see that looking along the length of the arc, there's no variation in terms of the isotopic composition along the length of the arc or related to the chlorine concentration. And then this is where these Columbia basalts, this transect lies. So it's been previously proposed that some of the possible sources for chlorine, maybe there's a small slab component, but we first looked at whether or not there's seawater or sea spray coming into them, whether there's any, we need to rule out any interaction with underlying sediments, or is there any interaction with these underlying basalts. So on the left-hand side, I've got, this is, it's cut off, I got boron concentrations on the x-axis, chlorine concentrations on the y-axis. The dotted blue line is seawater ratio. The solid black line is the Columbia basalts, transect basalts ratio. The red and the blue circles are the data from this study. The open triangles are previous work on different Cascade Springs by other folks at the USGS. The squares are Mount St. Helens Springs, and then this yellow area is gas condensates from Mount St. Helens. And one of the things that you can see is that most of the springs fall off the seawater line with the exception of Boswell. And so we've ruled out seawater and sea spray as the source of a lot of the chlorine. Also, most of the values are more positive than 0 per mil, so that also rules out seawater. We looked at underlying sediments. Marine sediments are isotopically negative. We get all positive values. So we don't think a lot of it is coming from the sediments. And so we started to think about these underlying basalts. And also, so the data aligns pretty closely with the basalts in terms of chlorine over boron. This is bromine right here, same thing. If you look at chlorine over bromine, they seem to match well with the basalts. So what I did was to just do some very, very simple isotope mass balance modeling. I'm assuming that water is infiltrating into the rock, it's reaching equilibrium, and you can assume different water-rock ratios. You can assume a starting composition for the different basalts and the waters and a chlorine concentration. And just doing a very simple mass balance diagram. Got chlorine concentration on the x-axis, chlorine isotope composition on the y-axis. The dots again are the thermal spring fluids. The black lines are basalts, and the gray lines are altered basalts. And the numbers on the tick marks are assuming different water-rock ratios. So what you can see that if you play around with the numbers a little bit, most of the values up to about 1.2 per mil can be explained by interaction of the water with the host basalts. There's a couple of values that are really high, and we interpreted this with a small magmatic component. HCl coming off of a magma body actually there's an isotopic fractionation, and it has a very high isotopic composition, and so if you get a little bit of addition of magmatic HCl, it can drive up those values. So, at least in terms of these thermal springs in Cascadia, I think what it's telling us about is local processes. These are local fluid rock interactions. We can explain most of the compositions based on interactions with the host basalts, maybe with a little bit of a magmatic component. But I was interested in seeing if we could trace what is coming off the subducting slab. And so then we went to New Zealand because they have these amazing cold springs that are on land that is easily accessible, that are only about 15 kilometers above the subducting slab. And so we don't have to worry about this high temperature fluid rock interaction as much. So yeah, so that was one of the motivations for going to New Zealand, because they have these cold springs. Most places where they get forearc cold springs are offshore. You need to sample them with a submersible, and especially if you're interested in halogens, you need to worry about contaminations of seawater. And so this is a diagram on the left-hand side. This is a map from Agnes Reyes and others. So we're looking at the east coast of the North Island, and all of these gray tick marks are different thermal springs along the length of the margin. And one of the reasons they're exposed here is you're subducting the Hickory Plateau, so you're uplifting the forearc, and so these are on land, which makes them easily accessible. This is a figure from Laura Wallace. And what it shows, the other reason I was interested in this is that as you go from north to south, along the North Island, we get a change in a lot of the subduction parameters. So one of the things is in the north, you have lots of seamounts that are subducting. You don't see that in the south. You increase the amount of sediment from north to south. You decrease the convergence rate from north to south. And what Laura's showing on here is the coupling coefficient. So in the northern part, you actually get very shallow, slow slip events. Where in the southern part of the island, you get strong plate coupling and you get more of a stick slip behavior. So you can get large earthquakes down in the Wellington. And so one of the things that I was interested in, and other folks have been interested in, is do any of these changes in the subduction parameters along the length of the margin affect what we see in terms of some of the seismic properties and seismic behaviors? It was also previously noted that by work of others is in these forearc springs, as you go from north to south, you see a change in the chlorine concentration, the boron concentration, sodium, and strontium concentrations. And so my question was, well, is that telling us anything about source that then may link to what is dehydrating that where, and if that can then be linked to seismic behavior? So the question is there a slab-derived fluid component to these forearc springs? Is there a change in the slab-derived fluid source along the length of the margin? And is there a link between the slab-derived fluids and this change in slip behavior that we see from north to south? And so in order to do that, I'm going to look at the cation and the anion chemistry, particularly focusing on the halogens, but also lithium and boron and their isotopic compositions. So we sampled over the course of 3 different sampling campaigns. Myself, my students, New Zealand collaborators, Sean Barker was instrumental in helping make this happen and contacting lots of, Stuart helped a little bit in contacting lots of landowners and speaking to the EV Council for us. And so as we went from north to south, we sampled 18 different spring systems. 2 of them are thermal, so Tapuya and Morari shown in the open stars, and then 16 cold springs, so the gray stars. And so this is what one of them looks. This is Mahia, which is located here. And so some of these have mud volcanoes with actually like little edifices, and other ones are just bubbling mud pits in the ground. And so part of the motivation for this work was precipitated by some previous work by other researchers who just gotten cut off, but by Agnes Reyes and others, and Gegenbach, and who they pointed out some of the trends in these forearc fluids. And so as you go from north to south, there is a decrease in the concentration of some of these elements. So there's a decrease in the chlorine concentration and the strontium concentrations and lithium and boron. The black circles are our data, and then the gray symbols are from the works of previous people. So we essentially just filled in a little bit of the blanks here. The other thing that stands out is that there are some places where you've got really spikes and high concentrations. So right here in chlorine and kind of in the middle part of the margin, and bromine and strontium, and in iodine. The dashed gray lines are those of the thermal springs. So we actually sampled 2 thermal springs. And what's interesting is that you see this high regardless of whether or not this is a cold spring here and this is a thermal spring. So they're high in both of the springs, regardless of temperature. So the question is, what is controlling this trend? And so one of the things we did was to look at different ratios. So looking at halogen ratios and also ratios with boron and lithium. These are all fluid noble elements, so it may tell us a little bit about source. So here I've got latitude on the x-axis, again going from north to south. I put seawater on each one of these diagrams just to kind of provide a reference point. And so we've got bromine and chlorine, iodine over chlorine, lithium over boron, and boron over chlorine. And so one thing that pops out at you is that there's not really a trend in the ratio from north to south. And if we start looking at what the different sources of these, so if we just look at bromine to chlorine or iodine to chlorine ratios of different reservoirs, this can be explained by any sediments overlap with this. But in terms of boron over chlorine and lithium over boron, both the sediments are off scale, slightly off scale. Then we thought about, okay, we're still at pretty shallow depths. Maybe it's not dehydrating sediments. What about sedimentary pore fluids? So things that are getting squeezed out of the slab at very shallow depths. So the orange is actually showing you the compositions of different sedimentary pore fluids. So at least in terms of the halogens, there's kind of overlap with both of them, so it doesn't really help us that much. We looked at boron or lithium pore fluids plot down here near seawater. So maybe we're having a mixture of pore fluids or dehydrating sediments. Another way that we can look at this is looking at this diagram that I showed you before, bromine over chlorine on the y-axis, iodine over chlorine on the x-axis. The black circles are our data. And you can see that they have a trend following along sedimentary pore fluids, also maybe that of sediments. They're all higher bromine over chlorine than what we see the altered oceanic crust, which is these diamonds down here. So it kind of gives us still this consistent story. So then we looked at the isotopic composition. So we looked at chlorine isotopes, boron isotopes, and lithium isotopes. Again, going from north to south, put the seawater on here for reference. Okay. Again, this was a surprise to me, so it stands out. It doesn't seem like there's much of a trend going from north to south. So we see this change in concentration, but we're not really seeing a change in the isotopic composition. And so what would possible sources for this? If we just again look at sediments, so chlorine or boron or lithium coming from dehydrating sediments. For chlorine, marine sediments can overlap this whole area. Boron have lower values, so it doesn't really match with sediments. Lithium, maybe these values down here. With lithium, it's a little bit harder to tell if these are actually coming from the dehydrating slab or if it's actually coming from the host rhyolachin. And then if we look at sedimentary pore fluids, marine sedimentary pore fluids overlap with sediments but get down to very low values. So again, this is consistent with dehydrating sediments or sedimentary pore fluids. Boron is almost completely consistent with sedimentary pore fluids. And then lithium could be a mixture of these. And again, I think a lot of this, these lower values, are due to local interactions and absorption and desorption. Yeah.
Just to make it clear, it goes all the way, right? It's not just, I know, it's confusing to me, that like the box extend all the way across the latitude.
Oh yeah, it extends
Yeah,
all the
it's
way.
not
I
just
just
like
put
that.
that on there because
Yeah.
I don't know if everybody
Yeah, I was
knows
wondering.
what the boron isotopic composition is of pore fluids off the top of their head. But yeah, it extends all the way across. Okay, so this was a little bit of a surprise for me. And so I think that how I interpret it is the stable isotope data, the elemental ratio data, is all consistent with sedimentary pore fluids or seawater. And so there's actually not a change in the fluid source going from north to south. So this change in concentration that we see is not due to some sediments are dehydrating in one place and not in another. But I think this actually has to do with fluid flux. I'll explain that in a minute. So it's not the source, but it's the amount of fluid. And I do think that, particularly in the case of lithium, there is some local modification by fluid rock interaction. We can talk about that in more detail afterwards. So it's been noted before, and so this is a figure that I modified from Laura Wallace and others, that in the northern part of the Hikarangi, you have extension in the north, okay, where you've got this upper plate extension, and so you get lots of faults, okay, and that there's higher permeability in the upper plate. So that means that as this plate is subducting and you're dehydrating the sediments, you're releasing the sedimentary pore fluids, they can go down and they come right back up, okay? So sedimentary pore fluids are sediments that are releasing this high amount of chlorine, high amount of lithium, high amount of strontium, go down and they just come right back up. But in the southern part of the margin, you get compression in the south. And so you don't have these big faults that allow for a passage of fluids. There's lower permeability in the upper plate, and so you still get subduction of this material, you still get release of these fluids, but they essentially get trapped and diluted by groundwater. And so this will explain the lower concentrations because there's this lower fluid flux because they're trapped and diluted by groundwater. And so the chlorine still could be coming from sedimentary pore fluids, and that's why it has that isotopic composition, but the concentration is just lower.
Is there any difference in the amount of sediments on the incoming plate that are scraped off that would also influence the amount of volatiles that go down?
Yeah, so in the southern part, there's more sediments that are being subducted. So you would expect that if the sediments are dehydrating, then you would actually maybe get a higher concentration in the southern part, but not in the lower part. But then there's questions of how much of the sediments are actually getting underplated and not actually getting subducted. And so there's been a lot of really nice geophysical work done by folks from GNS, and this is by Everhard Phillips. And I'm not a geophysicist, so I'm getting out of my comfort zone here. But one of the goals of margins is to really get geochemists and geophysicists and geodynamicists to talk together to answer common questions. And so this is a figure that shows. So here's the margin. So all of these different stars again are the springs that we sampled. And this is a map showing the QS, so which is the inverse of seismic attenuation at a depth of about 8 kilometers. So this is inverse seismic attenuation of S waves. And so low Q values, which are going to be in the red or the orange, are interpreted as high fluid content. Not necessarily high pore fluid pressure, but high porosity, and it's been used as a proxy for fluid content. So where you see the red and the orange, there's more fluids that are being able to be transported. And what's interesting is that a lot of these line up with our springs, and where we see some of the really high concentrations, or where we see some of this really bright red. And so there's distinct concentration highs that correlate with low Q values. And so I think it's a nice way to start trying to integrate geochemical and geophysical data sets. So one of the things that I want to do is then to look at the middle part of the floor. So we saw in Cascadia that these are mainly thermal springs, and that you get, with these high temperatures, you get a lot of fluid rock interactions, and so it's telling you about local processes and not much about the source. In New Zealand, to the very shallow level, so I think you're just getting a lot of sedimentary pore fluids that are squeezed out. Maybe we're seeing a little bit of dehydration of sediments, but then the question is, what about in between? So what about between like 20 and 40 kilometers depth? Do we start to get dehydration of altered oceanic crust? And so one of the things we're doing is starting a project looking in Costa Rica and some forearc springs on the Nicoya and the Osa Peninsula, which are also on land, but because of all these peninsulas that jut out into the ocean, you can still sample them at relatively shallow levels above the subducting slab. So in order to conclude or summarize, I hope I show you a nice summary of halogen inputs and outputs via arc volcanism are reasonably well constrained. There's still uncertainty regarding how much of the halogens are returning to the mantle, what is left behind in the slab residue, what is getting sequestered or stuck in the lower crust and upper mantle, and what are the timescales of that sequestration, and then how much of the volatile loss are we not taking into account in our mass balance calculations because it's essentially been short-circuited and lost through the forearc. In the very shallow part of the subduction zone in New Zealand, we look at expelled, a lot of the sources is coming from just seawater, or what I would argue would be altered seawater and sedimentary pore fluids, maybe some dehydrating sediments. And then in the deeper part, looking at Cascadia, maybe some magmatic contribution, but it's, the source is largely masked, at least the subduction source is largely masked due to fluid rock interactions. And that some future work will look at this intermediate zone, and maybe we'll start to see if there's more sediment dehydration or ultra-oceanic crust. And I leave you with a picture of Otokotogihi. Hopefully I said that right, I've practiced a lot, which is this, at the very, very north end of the North Island is this beautiful, it's almost like a lake where they have all of these little, like kind of mascot springs that we can sample, and it's a very sacred site to the memory. And they were very gracious to allow me to sample the waters, but I promised to bring them back. That was part of the deal. Yeah. Everything's supposed to go back to where it started, right? So, yes. So I'm happy to take questions.
I think I might just missed this. But
Okay.
Are you saying that the low Q value,
Yes.
right? Is it the because of the chemical reaction with the halogen, or you get more? Is it the other way? Like why? How do you get that low attenuation? Is it a structure base or chemical base?
It's structural. So the low attenuation, according to the geophysicists I've talked to, is interpreted as either high porosity or high connectivity of fluids. It's often interpreted as the presence of fluids, but it's not really telling you anything about like pore fluid pressure. So just more of a pathway for fluids interpreted as fluid content. And so where they see a lot of fluids at depth is also where we see the surface manifestation of springs, and where they have some of the lowest Q values, or where we get some of the highest concentrations. So it kind of matches with the interpretation that's why you get higher values, concentrations in the north, because that's where some of the low Q values are, and you're allowing more pathways for fluids to get through.
And then how does that affect? Because you talk about slip. Like
Oh, yes,
Does
yes.
that
So, Susan Ellis and Aki have done some work, and I'm getting out of my comfort zone. But yes, so thinking about how the higher, so more fluids getting trapped in the south can actually affect some of the seismic behavior, and I'm not going to explain it. So I can send you a couple of papers of theirs. That's not my work. Yeah. Yes.
So if I understood correctly, regarding the first part of your talk,
Yes.
So you look at the output at arc volume
Right.
by looking at degassing or
Yes.
looking at the concentration of the halogens in the local region.
Yes.
And part of the challenge is, yes, we do have halogens, but
Yes.
we don't know where they come from.
Right.
Exactly.
Right.
I was wondering if there is any studies that try to couple that with more like old school tracers of the source, like doing like strontium, neodymium, lead isotopic analysis of the forearc of the basalt, and just to see if they have more like a high new signals that would direct you to the oceanic crust, or EM2 that going to direct you to the sediments. I was wondering if some people try to couple these both.
Yeah. So there's been some work done on so I mainly think about chlorine, like ocean island basalts, coupling, looking at like subducted components of halogens and coupling it with other isotopic tracers. So there's been a little bit of that work done to try to look at, particularly if it's coming from subducted sediments or altered oceanic crust. And I can send you some of those papers if you're interested.
So do you remember if it's convincing, like basically?
Well, I'm convinced I've written some of them. Yeah, sure. Yeah, I mean, there's not that many studies out there, but I can send you. We can see if you're convinced.
So we're convinced that
Do we see, basically I was wondering if we see like a good correlation between IU signature and something that could have been interpreted in terms of the halogen as something coming from
something versus the mantle versus something that's been shoved into the mantle, is that the...
Or more, even more than that, like trying to decipher what exactly these fluids are coming from. Is that coming from the sediments, from the serpentinized mantle, or is that coming from the altered oceanic crust?
Yeah. So there is a little bit of work trying to figure out, if trying to link EM1, EM2, high view to subducted sources directly looking at halogens, mainly chlorine. But yeah. Yes.
So when you have the chlorine isotope,
Yes.
you have the value for chlorine isotope of the lava, right? That's
And the basalts?
Yeah.
Yes.
So that those are surface basalt.
Yes.
You just say lava.
Yeah.
Yeah. Okay.
Yeah.
And then
Yeah.
how do you know they're can chlorine isotope be diagenetically altered on the surface?
Oh, yeah, so we picked pristine, tried to pick pristine basalts, but yeah, so if you get, basalts that are altered to clays, like that will actually, you can get some fractionation during alteration. So yeah, we're trying to pick things that are unaltered. That's why I actually had altered basalt versus a pristine basalt, because it can change. Yeah.
So in the case of the fluorine not coming back up so
Yeah.
much, is there a fractionation between chlorine and fluorine in, say, the chlorites that are carried down? I mean, like Grove's model of some dehydration from the slab producing gritite chlorite. You get more fluorine-rich chlorite the deeper you go, so it's kind of sequestering the fluorine, and the fluids expelled are relatively chlorine-rich from dehydration.
Yeah, so most of the work that I've read is talking about fluorine that's being sequestered in the slab residue and anomaly anhydrous minerals. So there's been a lot of experimental work that shows that fluorine, way over chlorine, prefers to go into those. Also, titanoklinohumite has been argued as a host because it can also host large amounts of fluorine. Those are the two that I know of. Off the top of my head.
The amphiboles would do the same.
Yeah,
Yeah.
the role of
If I-
amphiboles too. Yeah, I was thinking.
But I thought like lower crustal, like really high-grade biotites are fluorine-rich.
Mhm. Yeah, yeah. But the explanation that I've seen for that disconnect is basically due to mineral host.
See, you didn't show delta D, delta 18 plots for those springs.
Yeah, because, so I have the oxygen isotope data. We just got the they're super salty, so they all had to be distilled, which took so long.
Oh, okay.
Yeah, but they essentially match what, Gegenbach showed, so they're similar to that. So you cover some of that.
So I can't remember, so what are they? They all look like seawater? Because you said
Yeah, they're not all seawater. He also argues that some of it is also a little bit of a maybe subducted sediment or dewatered sediment component, and so it matches that. It matches a little bit with that as well. So in our paper,
but it's not meteoric water.
no, not you can't explain it's not pure meteoric water. I think there's one or two of them that fall on the meteoric water line, but most of them we explain by addition of sedimentary fluids. Yeah.
Yeah, I was just wondering whether you might have analyzed some halogens for non-forearc or non-subduction related cold springs to just understand any effects that might be going on in the absence of the signal you're actually looking for.
Yeah, so the only cold springs that I've worked on are the ones in New Zealand. So, and then I've done some work on thermal springs in Cascadia. I'll talk about Yellowstone tomorrow, and Iceland. Yeah.
Other questions? Let's thank Jamie again.